the basics of a Pólya urn, and then move to the study of a bidimensional nonlinear and balanced urn models using two types of matrices. The first matrix is an irreducible one, and the second matrix is a diagonal matrix. The final section, I will treat the type of model of urn that is submitted to types of strategies. It means two strategies of drawing. So basically, an urn model consists in, given an urn containing two colors, basically the urn, the model consists in drawing a ball, check its color, and then return the ball to the urn according to the following. So if the ball drawn is of type red, then one adds to the urn, along with that ball, one adds to the urn one red ball and three black balls. And if the drawn ball is black, then one adds two red balls and two black balls. So this matrix that we constructed here is called the replacement matrix. It's a matrix according to which the adding of balls to the urn occurs. Notice here that the sum on the first column equals the sum on the second column equals 4. This constant in this example, this constant is called the balance constant. In this case, we say that the urn is balanced. So henceforth, the urn is set balanced with balance constant k if the sum on each column equals k. We denote by yn the urn vector composition at time n. The total number of balls is given by the sum, and the random addition vector xn is a random vector that represents the type of the ball drawn at time n. The classic drawing rule is given by this uniform quantity. This rule is called linear drawing rule. The urn evolution is described as follows. Given a replacement matrix, the number of balls of each color satisfies these following recursions, and the total number is given by this almost sure quantity. Now, what is the necessity of the balance condition? As you can see, the balance of the urn has a straightforward impact on the total number of balls, meaning that given a balanced replacement matrix, it means that the sum on the first column equals the sum on the second column. The total number of balls can read as follows. Then it is the deterministic quantity. I present here some of the urn models throughout history. So the first model is that of Pólya and Egenberger in 1923. They used a balanced matrix and symmetric and irreducible. After that, in 1940, came Bernard Friedman.
Please, the mic, please. Close the mic, please.
Okay, so in 1940, Bernard Friedman introduced a model generalizing the model of Pólya and Egenberger using a matrix that is still balanced but symmetric but irreducible. After that, in 1985, Bakshi and Pell, they broke the symmetry of Bernard Friedman using a matrix that is again balanced, irreducible, and non-symmetric. A recent model is that of Rafiq Agashiol in 2018. They used a reducible matrix, but non-balanced. As you can see here, A is different from B. Now, a natural question arises, what happens if the urn is no longer balanced? As we said earlier, that the balance of the urn affects the total number of balls, which makes it deterministic. Now, if we drop the balance condition, the total number of balls becomes non-deterministic, but rather random. That's why we need to control its rate of convergence. And to do that, we are going to use tools that are used by Henrik Roland in 2011. He studied urn models using the stochastic approximation algorithms. So according to Roland, a stochastic approximation algorithm Zn is an R-valued stochastic process defined by this recursion, in which the sequences gamma n, mn are Fn measurable sequences of random variables. The function h that is usually defined on the state space of Zn is an R-valued continuous function. And the following condition hold almost surely. There exist strictly positive constants C1, C2, Kz, Kh, Ke, such that these four bounds hold. So in order to prove a process that is a stochastic approximation algorithm, we need to prove these four bounds. As a matter of fact, the aim of stochastic approximation is the search of the stable zeros of the function h in order to establish the almost sure convergence for the process Zn. For that, we define the set of zeros of the function h given by theta star. So a zero y star of h is called stable if h is differentiable and the first derivative of h on that exact point is negative. Otherwise, it is called unstable. Now, once we've determined the stable zeros of the function h, we have this almost true convergence. We have this following theorem that states that if h is continuous, then Zn converges almost surely to a stable zero of the function h. We give here our the version of the central limit theorem introduced by Roland for a stochastic process Qn that verifies this recursion where gamma n hat un are Fn measurable sequences. And if we assume further that gamma n hat converges almost surely to a limit gamma hat that is greater than 1/2, and if the expectation of un squared given the past converges to a positive quantity, gamma squared, then we have this limit in distribution. Now we move to the second part of this expose, which is the bidimensional nonlinear unbalanced urn model. We start by the first case, which is the case of an irreducible replacement matrix. First of all, why the term nonlinear? As a matter of fact, I think it's in the work of Professor Hussam and Cuba. They defined a linear urn as follows. If the conditional expectation of the number of balls of type I verifies, given the past verifies this linear equation where alpha n and beta n are two sequences that depend only on the number of draws, then the urn is called linear. In 2019, Gilles Pagès and Sophie Laruelle, they introduced a new model called nonlinear urn model with a replacement matrix that is balanced, in which this assumption is no longer satisfied. So in the rest of this work, we will adapt the model of Pagès and Laruelle, except for one difference, that is our replacement matrix is no longer balanced. For that, we set this replacement matrix H, emphasized, first of all, on the fact that it is non-balanced. So the sum on the first column does not equal the sum on the second column. Second, we emphasize on the fact that the anti-diagonal entries are strictly positive, whereas the diagonal entries may or may not take 0 as value. The nonlinear drawing rule is given by this quantity for Zn I being the proportion of the number of balls of type I, where the function f is a continuous function that is defined on 0, 1, satisfying the following, which is f is non-decreasing, concave, and equals 0 on 0, equals 1 on 1. In this case, f is called a skewing function. Notice that if we set f to be equal the identity, then one retrieves the classic uniform drawing rule. So henceforth, we will set Zn to be the proportion of type of balls of type 1. Then Zn satisfies this recursion, where gamma n is given by 1 over Tn over the total number of balls. The mean field h, function h, is given by this form, and delta Mn is an adapted martingale difference. As we said earlier, the set theta star is the set of zeros of the function h. Then the set theta star is non-empty, and if y star is a zero of the function h, then it is in this specific interval, which we denote by I star. So if h, the mean field, then if h is continuous, then in the first case where we have this bound, then h has a unique solution in I star. In the second case, which is actually the complementary case, and if we suppose also that f is concave, then h has a unique solution in I star. Just a quick remark here, the concavity of the function h is only needed in the second statement, meaning that if we are dealing with the first case, we don't need f to be concave, any function will do. This result states that if h has a unique equilibrium point, then it is stable. We denote that unique stable zero by y star. For the proof, it suffices to see that h0 is strictly positive, h1 is negative, and if also h has a unique zero, then h is decreasing in the neighborhood of y star. Therefore, y star is stable. As we said earlier, the process Zn converges almost surely to a stable zero. And in this case, we have a unique stable zero. Hence, we have a almost sure convergence of the process Zn towards that exact zero. For the proof, if we want to prove that Zn converges almost surely to y star, we only need to prove that these four bounds hold. Now we give a result about the total number of balls. So the total number of balls, Tn, satisfies this almost sure estimate. For the proof, we need to write the urn vector yn in this form. Then after dividing by n, we see that this quantity naturally tends to 0. This quantity, using the fact that f is continuous on 0, 1, plus plus César's lemma, plus the fact that Zn converges almost surely to y star, finally we get this limit. And for the last part, we use the strong law of large numbers for conditionally L2 martingales, and again we use César's lemma to get this limit. We give now our version of the central limit theorem. For that, we set, first of all, gamma hat to be equal 1 minus rho star, where rho star is given by this quantity, and let sigma squared be given by this positive quantity. Then, in the first case, we have this normal distribution, this limit normal distribution. In the second case, and if moreover f is concave, we still have the same limit as soon as this quantity is less than 1/2. So for the proof, we recall that Zn can read as follows. Then we write Qn plus 1 in this form. Then we establish this new recursion where gamma n hat is given by these, gamma n hat and Un are given by these quantities. Then we prove that gamma n hat converges almost surely to gamma hat, which is given by 1 minus rho star. And we prove that the conditional expectation of this quantity squared given the past is converges almost surely to sigma squared. In the first case, if we prove that rho star is negative, then we get gamma hat is greater than 1/2. In the second case, we have rho star is positive. For that, we need to prove that rho star is less than rho star H. We move now to the part where we are dealing with a diagonal replacement matrix. So given this diagonal replacement matrix with A is different from B, this matrix coincides with the second case. So we need F to be concave. The associated mean field is given by this quantity. As you can see here, this form of function H already has two zeros, which are 0 and 1. So the goal here is to check whether H has an additional 0 in the open set 0, 1, and if so, on what conditions. This result confirms that if the function H has an additional 0 in the open set 0, 1, if one of the two following statements is satisfied. If f prime 0 is greater than this quantity in the case where A is greater than B, or in the case where B is greater than A, we still have f prime 0 is greater than this quantity. So as you can see, these two cases are symmetric. Now, if H has a third 0 in the open set, it means that a third 0 as other than 0 and 1, then it is the only stable 0. And if H has only 0 and 1 as zeros, then 0 is the stable 1 if A is less than B, and 1 is the stable 0 if A is greater than B. In this example, we will treat the case where A is greater than B, as I said before, that the two cases are symmetric. So we consider this concave function. This function satisfies our conditions, which are positivity and strictly increasing on 0, 1, and equals 0 on 0, and equals 1 on 1. Plus, we have that f prime 0 equals 2. So using these two matrices, we have these two quantities. The first quantity we call CH1 is given by, depends on A and B. The second quantity is given by CH2. So in the following graphs, on the first one, we see that our condition is satisfied, which is f prime 0 is greater than quantity CH1. Hence, we have 3 zeros, and y star is the unique stable 0. As you can see, H is strictly decreasing here. In the second case, the condition is not satisfied. F prime 0 is less than CH2. Therefore, H has only 0 and 1. And since we are dealing with a case where A is greater than B, then 1 is the unique stable 0. We give in this theorem the almost sure convergence of the normalized number of poles of both types. In the first case where H has 3 zeros, as we said, in this case, y star is the only stable 0. Therefore, we have these following almost sure limits. While in the second case, where theta star is only defined by 0 and 1, then on the first event, where Zn converges almost surely to 0, we have these following almost sure limits, where alpha is a quantity that is less than 1. And on the second event, which is again symmetric to the first event, the event where Zn converges almost surely to 1, then we have again these following almost sure limits. We move now to the last section, which is the nonlinear urn model submitted to two types of strategies. So before presenting the model, I would like to present a small preview to compare the first model to the second model. So in the old model, we used a deterministic matrix, whereas in the second model, in the new model, we are going to use a addition rule sequences that are identically distributed and independent, identically distributed, positive, and bounded. In the first model, we used a function, one function f, whereas in the second model, we are going to use two functions that depend on the type of the ball drawn. In the first model, f is strictly increasing and equals 0 on 0, equals 1 on 1. But in the second model, we are going to lessen these conditions to make f to move freely on the set 0, 1. Both functions f1, f2 to move freely on the closed set 0, 1. So we give the new definition. A skewing function f, a function f is called skewing function if it satisfies these new conditions. So henceforth, we let f1 and f2 be functions that satisfy the above definition. The f skewed drawing rules are given by these two rules that depend on the type of the ball drawn. Now we introduce the matrix, the non-balanced randomized replacement matrix that is given by this matrix, where the entries, as we said, Xi and Ig, are sequences of identically distributed, independent, positive, and bounded random variables with finite first and second moments, which we denote by mu Ig and sigma Ig.
Bounded is enough for the moments, huh?
Sorry?
The bounded condition is enough for the finiteness of moment.
Yes, I understand, yes. In this case, the mean field H has a unique equilibrium point if the following hold. In the first case, if these two quantities are equal. In the second case, if we are in the first bound, then one of the two statements is satisfied. If both functions are increasing or both functions are decreasing and concave. The third case is practically symmetric to the second case if both functions are increasing and concave or if both functions are decreasing. So H has a unique equilibrium point if one of these three statements is satisfied. So in this example, we will illustrate the existence and uniqueness of the equilibrium point. So by considering these two functions, f1 is given by this concave function, f2 is given by this linear function. And g1, g2 are given as follows. So the function f1, f2 are both increasing and concave. They satisfy the boundary conditions. Same thing for the functions g1 and g2 are both decreasing and concave, and they satisfy the boundary conditions. Using this matrix, non-balanced matrix, these graphs illustrate the fact that H still has a unique 0 in either cases. Now, once we've determined the stable equilibrium point, the unique stable equilibrium point, we have the following we have the following results. The first one states that the Zn converges almost surely to Y star, and the total number of balls satisfies this almost sure estimates. Now we give the estimates of the mean and the variance of the number of balls of each type. So the mean is given by this quantity, and the variance is given by this quantity, where where the function gj and fj are given as follows. We give here some of the examples to present a link with previous models. In the first model, we suppose that the replacement matrix is given by this anti-diagonal matrix, and we suppose that the functions are the identity. Then the mean of the first type of ball satisfy these estimates. the mean and the variance, where y star is given by this quantity is the almost sure limiting point for the proportion of balls of type 1. The second model, which is the Bakshi and Pell, as we said, they used this replacement matrix that is balanced. We have here the bound A plus B equals C plus D. Then the mean and variance are given by this quantity, where here y star is given by C over C plus B is the almost sure limit of the proportion of balls of type 1. For the weak rate of convergence, we set gamma hat to be equal 1 minus rho star, and where rho star is given by this quantity, and sigma, and we set also rho star mu and sigma squared given by these quantities. So the process Zn satisfies the following. In the first case, if f1, f2 are increasing, then we have this convergence, this limit in distribution. And in the second case, if f1, f2 are decreasing and concave, then we have this limit in distribution as soon as this quantity is less than 1/2. The second case is as we said, is symmetric to the first case. We present now another link with a linear model. We consider once more the following replacement matrix, this anti-diagonal replacement matrix. Notice here that these diagonal entries are equal 0, which makes us, in this case, also we suppose that f1 equals f2 equals the identity of 0, 1, then assertion a prime 1 of the previous theorem, a prime 1, this one, is satisfied. Then we have this limit in distribution. So now we move to the last part, which is an application to this model, the model of an urn submitted to 2 types of strategies. So this model was originally studied by Gonzalez and Lambert, as they considered a 2-colored urn, red and blue, and 2 different mechanisms of reinforcing it. Indeed, the 2 mechanisms consist in 2 players, player A and player B, using the same replacement matrix. The choosing of player is done by flipping a coin at each step. The matrix is balanced. The matrix used by Gonzalez and Lambert. The matrix is balanced, and the first column determines the balls to add if one chooses a red ball. The second column, B, determines the balls to add if one chooses a blue color. So before using the replacement matrix, player A draws a ball, then chooses with probability P the same color, and with probability 1 minus P the opposite color. Player B never draws a ball from the urn, but chooses blindly a color, red or blue, with probability 1 minus P and P respectively. Player A gets chosen, as we said, by flipping a coin, so with probability theta, therefore player B with probability 1 minus theta. And therefore we set this, Yn, the Bernoulli sequence that represents the choosing of player A or B. If player A is chosen, then given the past along with choosing in player 1, the probability of drawing a ball of type 1 is given by this quantity. But if player B is chosen, then the probability of choosing a ball of type 1 is given by 1 minus P. So combining these two quantities, we get that the probability of choosing a ball of type 1, given the past and any player chosen, is given by this quantity. Since Yn is an independent Bernoulli sequence with parameter theta, we get that the probability of choosing a ball of type 1, given only the past, it is given by this quantity. Naturally, the probability complementary probability is given by 1 minus the previous one. So we suppose that Zn is represents the proportion of balls of type 1 or type red. Then we set these two functions, f1 and f2, which are given by these linear forms. The drawing rules are given by these two rules. Here, since f1 plus f2 equals 1, then the functions f1, f2 are of the same monotony. If p is greater than 1/2, then both functions are strictly increasing. If p is less than 1/2, then both functions are strictly decreasing. And if p equals 1/2, then both functions are equal 1/2. The concavity assumption is satisfied since the functions f1, f2 are linear functions. The boundary conditions are also satisfied, as you can see here. Now we consider this randomized unbalanced replacement matrix that is given by sigma, which is in this set. We set then this mean matrix, which is given by gamma, which is the mean of the matrix sigma. Now, since the replacement of balls depends on two players, there are four possibilities. The first one, picking a red ball using the first column, which is done by either player A or player B. Then the probability of picking the first column equals this quantity. If a red ball is picked and using column, and we use the second column, then the ball is picked by either player B, player A, or player B, then the probability of the first column, of the second column is equal this quantity. With the same reasoning, we get, these are the means of the two quantities of the means of these equalities. With the same reasoning, we continue to present picking a blue ball and using the first column, or picking a blue ball and using the second column. We have that the mean of the first and the second column are given by these quantities. Finally, the mean field is given by this expression. And as you can see here, mu1 is different from mu2, which is the sum on the first column, and this one is the sum on the second column. Therefore, here, as you can see, the matrix, the mean matrix is not balanced. The first result states that the set theta star is non-empty and H has a unique stable 0 in 0, 1. Plus, if Y star denotes the unique stable 0, then the process converges almost surely to Y star. For the proof, first of all, we start by proving the existence. As you can see, H is continuous and positive, strictly positive on 0, strictly negative on 1. For the uniqueness, after some computations and comparison between these two quantities, we get that this quantity equals, depends in fact on the entries of the matrix along with theta and P. So a discussion about on the value of P. If P is greater than 1/2, then we satisfy condition A2 and A1 of the theorem. And if P is less than 1/2, then both conditions B1 and B2 are satisfied. Now, if either P equals 1/2 or this quantity equals 0, then these two quantities these two functions equals 1/2, and then condition 1 of the theorem is satisfied. For the stable equilibrium point, since it is unique, it is stable, as we said in the first part of this expose. Finally, the stochastic approximation theorem guarantees that the almost sure convergence guarantees that the process Zn converges almost surely towards Y star. Now we present a link with previous models. If theta equals 1 and P is in the set 0, 1, and if the replacement matrix D is anti-diagonal, then we retrieve the model studied by Rafiq Agash et al. If the replacement matrix is balanced, and then for starters, we have that Zn converges almost surely to this quantity whenever k minus theta multiplied by mu11 minus mu21 is positive, of course. Hence, we have the following. If theta equals 1 and P is in the set 0, 1, we retrieve the Bakshi and Pell urn model. And if theta equals 1 and P is again in the set 0, 1, and moreover, if the replacement matrix D is anti-diagonal and balanced, then we retrieve the classic generalized Pólya urn model where Zn converges almost surely to 1/2. Finally, the case where theta equals 0 and P moves freely on the set 0, 1. This case boils down to the case where this quantity is equal. Now we give the strong law of large numbers for the total number of balls. As you can see, Tn satisfies this quantity, this almost sure estimate, where alpha and beta are given by these quantities. For example, if theta equals 1 and P equals 1, we retrieve the classic model introduced in Rafiq Agash et al. For the CLT, we set gamma hat that is equal 1 minus rho star, where rho star is given and sigma squared are given by these two quantities. Then the process Zn satisfies the following. If this quantity AD minus BC is less or equal 0, then we have this limit in distribution. Again, if AD minus BC is greater than 0, then we have this limit in distribution as soon as this whole quantity is less than 1/2. For the proof, recall that this quantity, mu11 multiplied by mu2 minus mu1 multiplied by mu1 is equal this quantity that depends on theta and P and the difference between the entries of the matrix. So at first we suppose that AD minus BC is less or equal 0. Then we have the following two cases. In the first case, if P is greater or equal 1/2, then F1 and F2 are increasing. Then statement A'1 is satisfied. In the second case, if P is less or equal 1/2, then statement A'2 is satisfied.
Please, the mic, please. Close the mic, please.
So in the second case, where AD minus BC is greater than 0, then for all P and theta in the set 0, 1, we have rho star is greater than 0. Therefore, we have to prove that rho star is less than rho star mu. Therefore, we fulfill the conditions of the two statements B'1 and B'2 of the CLT theorem. And here are some references. And thank you for your attention.
Very, very nice talk, Soumaya. Congratulations. Thank you.
Some water.
Thank you very much.
Thank you, Professor.
We go now to questions, please. Someone have some questions?
Thank you, Soumaya.
Thank you, Professor.
Yes,
Andy.
okay. Thank you for your presentation that contains a huge of information. So,
yeah, I struggled with the way of putting that amount of information in too less of slides.
Okay. So my question deals with the replacement matrix H. You give some conditions. Can you replace this condition by the nature of the matrix if it is invertible or singular or diagonalizable or not diagonalizable? This is my question, my first question, maybe.
Actually, I was interested in two cases.
It is more easier for a reader to understand this condition by the nature of the matrix is if it is singular or especially we see AD minus BC, so it is a determinant. Okay.
Yeah. Yeah, it's are you talking about this matrix H or the last one?
The replaced in.
Listen,
for example.
okay.
Okay.
Oui.
Excuse me. Yes. Okay.
Okay. As a matter of fact, est-ce que je peux parler en français ou en anglais comme vous voulez? Hein?
En anglais, please.
Okay. Okay. As you see, the only condition that is required on the matrix is that is non-balanced. It means that the sum on the first column does not equal the sum on the second column. This is the first condition. Other than this, the type of the matrix, it differs from a reducible 1 to an irreducible 1. These are the only two conditions that I used.
Okay. And I remark that Zn can converge to a constant, not a deterministic variable, not a random variable.
Yes,
because usually in your model, the limit is random variable. But here we observe that it may be a deterministic.
Yes, as a matter of fact, it's deterministic, as it is the zeros of the function h.
But for example, for the simple model, the ratio of the converge to the uniform distribution on 0, 1. But here we observe that the limit is deterministic.
And the conditions, the limit of proportion must converge to a deterministic limit and the conditions of Soumaya.
Okay. Very interesting to thank you.
Thank you. Thank you.
Other questions, please? Yes, Dr. Rashid Assel.
Thank you, Rafiq. First, I want to thank Soumaya for his interesting talk.
Thank you. Thank you.
I have a question of a non-specialist. بالعربي متطفل. Is there any algorithm, computing algorithm that can be used to test the convergence of the processes you are studying? I mean, many things I heard in your talk are look as processes. So can these processes be implemented in a computing algorithm so one can see with a computer the convergence or the divergence of the process? That's the question.
Professor, you mean that if I can use this algorithm in a computer in a program to see the convergence using a program?
Yes, to test the convergence.
I think it may be done, but I don't know how actually.
Okay.
Yes.
Thank you.
Sure, it can be done. Sure.
Yes, it can be done. Actually, it's my next project. I would like to use a program to test the convergence using maybe the R program.
Other questions, please.
Bonjour.
Yes, Philippe.
Alors, je vais mettre la caméra, mais ça ne marche pas. Donc, désolé. Donc, merci Soumaya pour l'exposé.
Merci.
So, with respect to the replacement matrix that we see, quite often it's possible to get different limiting behavior in terms of the eigenvalues of this matrix. For example, if one of them is larger than 1/2 or stuff like this. And later in the talk, you had some condition with some type of cross conditions for the centers and so on. So is it possible to have a link between some properties of the eigenvalues of this matrix and some of the theorems that you gave?
Je suis vraiment désolée, Monsieur Siri, je n'ai pas vraiment entendu votre question. Excuse me, can you please repeat it?
Okay. Donc en français, si tu veux. Est-ce que tu as des liens entre les valeurs propres de cette matrice H? Parfois, il y a des conditions comme quoi si la valeur propre est plus petite que 1,5 ou des choses comme ça. Et certaines des propriétés que tu as données après, des conditions que tu as données après sur des relations entre ces coefficients.
En fait, en utilisant l'algorithme stochastique, je n'ai pas eu recours aux valeurs propres de la matrice. Hein.
Effectivement, elles n'apparaissent pas dans ton exposé,
ouais.
Mais est-ce que…
Parce que je ne l'ai pas utilisé.
Mais est-ce qu'il n'y a pas certaines des conditions que tu as données par la suite qui en fait peuvent se réexprimer en termes de propriétés sur ces valeurs propres?
Soumaya, can you give the answer in English, please?
Ah, okay, yes, sorry, it's my fault also.
So your question is whether if I can find conditions about the eigenvalues of the entries of the matrix?
Yes, which will be a kind of, which will possibly rephrase some of the conditions that we have later. Because it is very frequent for Pólya urns that many theorems can be, they have a condition if the eigenvalue is larger than 1/2 or smaller than 1/2.
Yes.
Like
yes.
this. So perhaps that in some conditions that you have later, it could be in fact hidden or equivalent to this condition. I'm not sure. Huh?
Yes, but historically in the literature, I found that using eigenvalues are only used in studies that does not involve stochastic approximation algorithms. But I honestly don't know. I honestly did not check.
Okay.
Sorry.
Other questions, please?
Hello, Soumaya. Could you please go to slide number 40, 40?
40. This one?
Yes. Once again, one more, please. Just click. Okay. In case rho star is negative, then gamma hat is bigger than 1/2.
Yes.
But
as you can see here, if rho star is negative, then this whole quantity is bigger than 1.
Yes, it's okay.
Then automatically is greater than 1/2.
Okay, and you need this condition.
Yeah.
Gamma hat bigger than 1/2. Okay. Further, in 28, please. 28.
28. This one?
Okay, F is defined on 0, 1. Because if it were defined on, if it was concave on R plus, not only on 0, 1, then automatically it will be not decreasing.
Excuse me?
If no, nothing, because if F was concave on R plus, but on 0, 1 only, then it will be systematically non-decreasing. Okay, no, there is no ambiguity here. Okay, thank you.
Thank you.
What happens if we have more than one stable zero?
Okay, what happens if we have more than one stable zero? Actually, this is my next project. So at this stage, I'm not able to determine exactly what happens, but I might have an idea, probably because the process converges almost surely to a stable zero. It means that the probability of converging to a stable zero is positive, strictly positive.
Mhm.
So, in order to determine which one exactly is the limit, or which one is the limit with a probability, actually, I'm stuck at this stage. I have no further information. So I think that it will involve the stopping time, or the time of entry of a process in a certain interval.
Okay. Okay. Other questions, please.
Alors, potentiellement, oui. On these slides, so you said that for sure, if you are taken F, the identity function, then you are going back to the uniform model, the classical uniform model for the drawing of the colors. Yes, exactly, this is what I mean. And did you consider some specific value of F which could lead to some perhaps possibly nice combinatorial model?
Excuse me, that leads to what?
To some possibly nice combinatorial models.
I don't understand.
For example, could you take F equals X square or something like this?
Okay.
Condition?
You mean
so that could...
if F, for example, equals X squared, then it is convex, right? So the case of F where F is convex is a whole another case that I am working on actually right now. And it gives more than one stable zero, which is in fact exactly the question of Professor Rafiq.
Okay, yes. So here it was.
Yeah, it's delicate. It's more delicate than the fact than F being concave. It may give 5 or 6 zeros.
Okay.
Other questions? Hi, Hanan.
Bravo, Soumaya, c'était très bien. But one question, please. One naive question, Soumaya. Do you have an intuitive explanation for the convexity assumption necessary for the uniqueness of the mean field equilibrium point? Slide 13, I think.
Actually, the naive questions are the most scary one. Excuse me, slide what?
13. 30.
This one.
One click, yes. Why this concavity or convexity assumption in this case? An intuitive explanation, why?
Well, actually, the concavity and the convexity assumptions, they were introduced by those originally introduced the model, who's Sophie Larbial and Gilles Pagès. They used the convexity and the concavity to model the risk variation. So the concavity is used to model the risk aversion, whereas the convexity is to model the risk seeking. But here, if we delete this concavity assumption, we have no information about H. So the concavity here, it helps to better see the zeros of the function H. Actually, I tried to work on this condition without the concavity, and I got stuck for like 3 or 4 months. Finally, I gave up.
No, you have to continue, so Soumaya. Thank you.
Thank you so much.
Good luck.
Thank you.
And thank you, Rafiq, for the invitation.
Thank you for you.
It's nice to meet you.
Thank you.
Other questions? So, Soumaya, really, your talk and your answer to questions are perfect. Thank you again. Thank you for this nice talk. Thank you for all the public and see you next week. Thank you, Nabil. Thank you.
Thank you, Rafiq. And it was a really very good idea to invite Soumaya, because she show how she is mature and really it was very good talk, even if it's not my specialty.
Nabil, Hanan Mohammed is our colleague from the University of Monastir, Paris, and next year she gives us a talk, inshallah. Okay, Hanan?
We will discuss the topic.
Okay.
Hanan, okay, you're welcome. Yes, Hanan.
Thank you.
Okay, thank you again, Nabil.
Okay.
See you.
Okay, I record the talk and I will put it on the website. And please, Soumaya, she is not with us. If she can send the slides, please.
Okay,
Okay, thank you, Rafiq.
منى العياشي تعرفها نبينا؟
لا
منى معنا mon collègue de l'université de Monastir. أهلا منى.
أهلا صباح.
الحمد لله جيت بريزونت منى العياشي نبيل.
مرحبا بها.
مرحبا. نبيل peut-être نعرف سيرين قماتي.
Bah, c'est ma cousine.
C'était mon ami d'enfance, Hasra.
Ah, d'accord. Bah, c'est ma cousine.
Sinon, j'aurais bien aimé vous connaître directement.
Inch'Allah, on va avoir l'occasion de se rencontrer.
Bravo pour tout ce que vous avez fait là. C'est vraiment très surprenant, agréablement d'ailleurs.
Bah, c'est un travail collectif. Ça ne peut réussir que parce que c'est collectif.
ان شاء الله تبقوا معنا منى ان شاء الله.
ان شاء الله اوكي.
هذا ما كانش على بالي بالويبينار منى.
اي لا مرحبا.
ورشيد عسل الوصي. الله الى اللقاء.
الى اللقاء.
Au revoir tout le monde. Salam.
يا نبيل.
Oui.